dad went to a show. They dropped me off at Grandpa Joe's. I kicked and screamed, said please no. Grandma take me home, 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 Grandma take me home. I had to eat my dinner there, mashed potatoes and stuff like that. I couldn't chew my meat too good. Grandma take me home, 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 Grandma take me home. Said my dog, stop crying, go outside and ride your bike. That's what I did, I killed my dog. Grandma take me home, 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 Grandma take me home. After dinner I had ice cream. I fell asleep and watched TV. I woke up in my mother's arms. Grandma take me home, 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 while I feel alone.
All right, so everybody had a successful first lab yesterday where we walked you through the basics of writing a very basic Hello World program, compiling it and running it. And I just wanted to take a few moments at the front to go through that process in a little bit more detail because there's a whole lot going behind the scenes. When you type out GCC and it compiles something, it's actually doing a whole bunch of stuff. It's going through preprocessor directives. It's going through, it's optimizing stuff. It's removing comments. It's then translating that high-level C code into what's called assembly. And then finally, that assembly is translated into binary machine code, zeros and ones. So let's go ahead and start out with a little bit more substantial program here. This program is called KMS to miles. And so because of the name and because of the documentation up here, you can say that this program converts miles into kilometers, right? It's pretty basic. What it's going to do is it's going to, let me go ahead and get rid of this for a second here. It's going to prompt the user to please enter the number of miles. The user, us, will enter the number of miles. It'll do a computation. It'll multiply by miles by kilometers per mile, etc. And then it'll output the result. This is a basic input-output program. It's prompting for input. We're giving it input. It's producing output. So let me go ahead and just GCC this all at once, like you did yesterday. And that will produce an a.out file because it's a syntactically correct program. If we were to run this, it says, please enter miles. Now it's sitting there waiting for us to actually mash the keyboard and then hit enter. So let me just say 12 miles here, enter, right? 12 miles is equal to 19.312 kilometers, okay? So now that we understand what the program is doing, let's go ahead and walk through that process, but in a little bit more detail. And the detail that I want to show you first is, let's go ahead and compile it to assembly here, all right? Ultimately, that a.out file, that's not something that we're going to be able to look at, right? But if I go GCC and use this special flag, -S, what I'm doing is I'm telling GCC, don't do that entire process. Just do the process of converting C into assembly code. And it's KMS to miles. There we go. And let me go ahead and type ls again to list everything. You'll see here that there's KMS to miles.s. That's my assembly file over here. Remember, sometimes it doesn't sync, so just go ahead and hit that refresh button, and you'll see it over here. Let's open it up. It's also a plain text file. but it is far less readable, right? There are these weird commands all over the place. Move Q, LEAQ, move L, call, et cetera, right? This is assembly, right? And this is what existed before C, okay? Basically what it's doing is it's saying, move this, whatever's contained in this register over to this register. Compare whatever's in that register to that register, and if they're equal, jump to this memory location. It is much, much lower level kind of commands. Basically, we're telling the processor directly what to do, right? We're saying load up that thing into that registers or memory addresses on the processor itself. You can look at it like that. It's far more complicated today, but that's the basic idea, right? That is still not something that is readable at all, right? If you just saw this, you would not get the same impression as if you had read this, right? This is pretty easy to read. It prompts for miles, makes the computation, and outputs it. This is far harder to read, right? But you could still write in assembly. And back in the day before C, people wrote in assembly. Even before that, they wrote in binary. So now let me go ahead and ask GCC to compile this into KMS per miles.c. Right? And now another file is produced here. This O file, this object file. That is pure binary. Okay. If I were to try to open that, in fact, it wouldn't let me because it says this is a binary file. Do you really want to open this? Open anyway. I'm going to have to find a text editor that handles binary. Instead, I'm going to show you a utility that handles binary here, hexdump. And let's go ahead and go with C KMS to miles.c. Right? There you go. So now what we have over here is a memory address and then a bunch of hexadecimal. Hexadecimal, we're in decimal, base 10, because we have 10 fingers and 10 toes. Computers are base 2, 0 and 1. But you have other base systems. One compact base system is hexadecimal, which is 16 characters, 0 through 9, and then A through F. Right? Don't worry about the details. You're not going to have to convert or anything like that in this class. Did you have a question?
Oh, I was just going to ask if you meant to do .c instead of
Oh, sorry. Dot O. Okay, thank you. Let's do that .oo object file. There we go. There we go. Now it's far less readable, right? But some of this stuff is readable, like GNU stack. I wonder what that is. It's some internal thing. That message, please enter miles. We can still see that, right? That's not binary. I mean, it is binary at the end of the day, but it's something that is readable to a human. But the rest of this stuff is completely not readable by a human at all because it is meant for a computer, right? Now that .object file is still not runnable. If I tried to do, like I did ./KMS to miles, it's not even going to let me tab over there. What is it? .KMS to miles.c or .o, right? Permission denied. That's not something that's runnable. There is yet another process that happens. It links into a bunch of stuff. For example, we are bringing in these external libraries, the standard input-output library, because it has this printf function and the scanf function, right? We didn't write those, and it's not part of my object file here. It's part of some other object file that has already been compiled for the system. So GCC is going to, as a final step, is going to take all those things, link them together, and finally produce an a.out file. That entire process that I gave you is still oversimplification. There's still a whole bunch of stuff that's going on behind the scenes. If you ever get into a compiler class, maybe you'll see some of it. There's optimization, there's preprocessor directives, et cetera, right? I wanted to show the same process over here in Java, right? But with Java, our IDE, our integrated development environment, it's making that entire process completely opaque, right? We don't see it at all. We type out here, and then we just hit this button up here in this nice graphical user interface, and it says hello world, right? But on the system in the background, there is a bunch of stuff that is compiling Java into what is called Java bytecode, and then that bytecode is actually run on a Java virtual machine. It's being done automatically. Like, for example, if I erase that, then the compiler is automatically recompiling, sending back information that there's a syntax error, and that's why we get some red here, right? If you actually look on the system, let me go ahead and show you how you can do that. I'll go ahead and, let me go ahead and go to the top level here. If you right-click your project and go to Properties, right, it'll actually tell you where it's stored on your system, and you can actually click this button and it'll take you there. Right? There we go. All right, there's where my Hello World project is being stored. If I look at src, unl, soc, and then I see my source file there, right? Now, why did I have to go to source? src is short for source. Why is it in unl and then a subdirectory of that called soc? Because over here, that's what I programmed it for. I put it into a package. So those packages are nothing more than folders, or more, the regular people call them folders. We're computer scientists, we call them directories, right? And so those are directories, right? And there's my Hello World program that we see over here, right? I don't want to look at that though. I want to see what's actually being run. So we have bin. What do you think bin is short for? Binary, right? And we have the same directory structure here, unl soc being mirrored. We have this hello world.class. That's the Java bytecode that has been produced. In fact, I can if I've got hex dump, I can show you what it looks like. There we go. Hex dump. Let's go with hello world.class. There it is. It's also a bunch of binary, right? In fact, if I go hex dump with another flag here, C, then we can see some of it, right? Some of it's readable, but for the most part, most of it is not readable at all. It's machine code. In this case, it's special machine code. It's not machine code that runs on the processor on my Mac. It's machine code that runs in another program called the Java Virtual Machine. The Java Virtual Machine runs on the processor on my Mac, right? The entire history of computing is nothing more than adding abstraction on top of abstraction on top of abstraction. The reason that we have Java is because they wanted a universal language back in 1995. They wanted a language that could be written once and then could be compiled once and then run on any machine that had a Java virtual machine on it. It was a virtual machine on top of that machine, right? So now Python, we have Python is an interpreter, right? That runs on top of a bunch of other stuff. Right? We're trying to get away further and further and further away throughout history from the actual, hardware, the metal that we don't want to deal with that basically, right? Why? Because back in the day, you had to actually program in zeros and ones, punch cards. You'd punch it out and it'd be a 0, you'd leave it and it'd be a 1, and then you fed that into a machine. How tedious was that? So that's why they created assembly. How tedious was assembly? Well, that's why they created compilers and higher level programming languages. How tedious were those to write a compiler for every different system? So that's why they introduced Java, right? And so each innovation is a step away from the actual physical hardware. All right. Any questions on that process? I'll show you processes as we go along here, but you won't be dealing with assembly or binary or any of that kind of stuff, right? And as I think I already went over this, but Java is not a purely compiled language. Instead, you compile it into what's called Java bytecode. It's a machine-like language that's runnable on a Java virtual machine, and then the bytecode is actually interpreted by the JVM, or the Java virtual machine. All right, for the rest of the day, let's go ahead and look at that program that we just saw in C, right? And let's go ahead and start from the top. Let's see, where are we? There we go. Let's go ahead and start from the top and work our way down and look at the anatomy of a more complex program. This is still a very simple program. What do we have at the very top here? What is this? It's a comment, right? In fact, it's a special kind of comment. It's a multi-line comment that begins with a / and ends with a */. It's even more special because what I've done here is I've put a nice vertical line of stars here. This is what's called a doc style comment. Doc's short for documentation. It's a documentation style comment in which I'm putting the author, the date, and the purpose of this program. We're going to be grading based on documentation. So in your hacks, you need to include documentation like this. To start out, we're just looking for this, an author header, right? We're always going to be requiring an author header for all the hacks that you turn in. If you worked in a pair, right, then make sure that both of your names are in there. But that's the purpose of this doc style comment, right? So more generally though, what are comments? Comments are for humans, right? They're not for programs. They are ignored by the compiler. They are intended for other humans to read, why are you doing this? What is the purpose of this program, right? The purpose is to communicate to other humans why you did this or what your intent was, because you might have got a bug or something. And even though you say it does something, it doesn't actually do that because there's a bug and you still need to fix it. But that's what the documentation is for. It is for the what and the why, not necessarily the how, right? This program is going to be converting miles to kilometers. It doesn't tell us how it does that. Well, there's this special value 1.6 blah, blah, blah that it multiplies by after reading. And right now, we don't want that in the documentation. We don't want to be repeating ourselves. There's a DRY principle, by the way. So every time I'll always take an opportunity to introduce acronyms because our discipline is a very acronym-filled discipline. This is don't repeat yourself, right? So don't repeat unnecessary things. The how here, that's going to be the program. After a couple of weeks of programming in C, in fact, maybe right now, you can look at this program and tell how it goes about doing what it's doing, right? Instead, your comment should be the what and the why, not the how, right? For now, what we're all looking for is a header, right? Instead, code should be self-documenting, right? And what does that mean? It should be clear enough. It should be clearly written enough so that anybody who knows the language and knows what they're doing understands what's going on, right? And I don't have any other comments here, right? You don't see any other comments here. I don't want to see any other comments here, because if I had another comment here, like for example, declare the variables I'm going to use, right? This is a bad comment, right? Anybody who knows the language can see that you are declaring variables there. Another one would be, read in input from the user, right? No, I can read these two lines and see what that's doing after I've been introduced to the language. This is what's known as cruft, right? Have you ever heard that term before? Cruft? All right, so another term here. It's not an acronym, but it's still the same, cruft, right? Useless or verbose code, right? Basically, it comes from, I don't know if it's Harvard or Yale, but the legend is that there was a building called Cruft Hall, and it was disused. There were no classes in it anymore. And so what would happen to it? Well, I've got a broken projector. What do I do with it? Well, you throw it into Cruft Hall, right? And eventually the building filled up with garbage, right? And we don't want our code to be like that. We don't want our code to be full of garbage. These kind of comments, if you write them, those are unnecessary garbage. That's cruft. Get rid of them, right? Because your code should be self-documenting. Once you know what printf does, once you know what scanf does, then you don't need those comments as we go along. Now, if for demonstration purposes in lecture, I will probably be a little bit more liberal with my comments, just so that you get the benefit of what this does. But in your code, you shouldn't be doing that. You should stick to the what and the why, not the how. It should be self-documenting, okay? All right, what about the syntax? In fact, we're not gonna have any difference in syntax from both languages, C and Java, right? Single line comments are those backslashes or forward slashes? Forward slashes because the guy's leaning forward, right? Multi-line comments use or begin with, let's say begin with /* and end with */ and everything that is ignored between those two things. Single line comments use that, but once you go to the next line, then you're back in code land, right? This only ignores everything to the end of the line, right? Sometimes I'll have typos, sometimes I'll correct them, sometimes not, right? So for example, I could go ahead and put a comment at the end of the line here. This is a single line comment, right? But if I went down to the next line, You can see from the syntax highlighting there, it's no longer green. Now I'm on the next line, and that's a comment that's not being ignored. So single line comments, and then multiple line comments would look something like this, right? You can use multiple lines here. Yay. Right, there we go. And there's a multi-line comment. A very special multi-line comment, as we already just said here, was a documentation style comment, where you have this nice vertical line of aligned stars and the documentation that goes with it. And guess what? Your IDE will do that for you. Go /**, enter, and it will automatically put those vertically aligned stars for you. Hello, how are you? Right? Okay. I'm going to restore what we had before, but it's something that you should let your IDE do. And Eclipse does the same thing. Every IDE will do this. As we just started out with /**, it'll know you want to write a doc style comment, so it'll automatically format that for you. Okay? All right. Please stop me if you ever have any questions, though. None so far? Yeah, go ahead.
When you put the things into a package, why do you put them into unl.soc? Why the extra folder there?
Generally, you want to separate things out and organize them. And I just chose UNL-SOC because usually you have an organization, right? For example, I don't know, Apache. Apache is an organization with a lot of code. So they have Apache, and then they have web-related stuff, apache.web, apache.utils, basically it's a hierarchical thing. Up here is the big organization, UNL. Then down here we have SOC, School of Computing. Over here we could have physics, right? And so I just needed to choose one. If you don't have that, by the way, over here in Java, packages are Java only, by the way, then you have what's called the default package, right? And if you put all of your code into the default package, now you start to get conflicts, right? Because what if you had two Hello World programs, or just as a dumb example, but what if you had two lists, right? Now they cannot coexist. You can only have one Hello World program in one package at a time. So it's a way of organizing code. Okay. Does that answer your question? All right, good. Yeah, go ahead.
When should you use like standard single line versus multi-line comments versus doc style comments?
So later on, when we really get into functions, every function will need doc style comments. Every class should have an author header. Every C program should have an author header at the top. Generally, it's all going to be dictated by whatever style guide you use. And there are multiple competing style guides for C. There's the GNU style guide, there's the Google style guide. When you move on to an organization, you're going to be, if you're doing C, like Garmin, it might have their own style guide. You might be forced to use the Garmin style. And so there would be directives on what you do when, right? Generally, though, for this class, for now, we're just looking for an author header. When we get into like week 5 and we start writing functions, then we'll talk about doc style comments for those functions. Okay. So, next. What do you see over here? Come on. On line 7 and 8. What are those? Yeah.
Those are preprocessor directives to include these
standard library and
the
standard input-output library, right? Exactly, those are preprocessor directives. The C compiler has what's called a preprocessor that processes your code before it actually goes to compile it. Preprocessor directives always begin with a hash, right? By the way, do we know why it's called the hash? It's just 2 vertical lines and 2 horizontal lines. Right?
It has something to do with hash browns.
Exactly, it does. How are hash browns made? You cut them up. So and then you cut them up this way, right? And then you put a batter or what, I don't know, I've never made hash browns. But that's exactly, that verb there, to cut, is called hashing, right? And so that looks like a hashtag or a hash mark or whatever because it's been cut vertically and then cut horizontally, right? Just something that, fun to think about. Why do we call the stuff what we call it, right? And that's because it's hashing, right? You can include external libraries using the include preprocessor directive, right? Generally, these are going to start or end with a .h. That stands for a header file. We'll understand that later when we start writing our own header files. Basically, what it does is it goes out to that header file, copies everything in that header file, and then pastes it into your source file. That's what the preprocessor is doing. That's just so that you don't have to manually keep hundreds or thousands of lines of code that you don't care about in your program, right? You can put it over here in this other program or over in this source file, and you can just, bring that stuff in, right? So that you don't have to repeat yourself. Again, it goes back to the DRY principle. Don't repeat yourself. Organize code by moving common code over to this other file so that multiple programs can use it. And so that you don't have this one big giant file with millions of lines of code, right? It's a way of organizing stuff. Another one that you'll eventually use is including math.h. You have access to basic functions like sine, cosine, sqrt. What do you think that is? Square root, exactly. Why do we call it sqrt? Why didn't we call it square root, right? Yeah.
Because it's too long.
Exactly, it's too long. Think back to when this was created in the 70s, right? Square root, that's a lot of letters, right? We don't have megabytes of memory, right? We have maybe bytes of memory or kilobytes of memory, right? So if we can shorten something down and save on bytes back in 1970s, right? Then we did that. We're still living with that today, by the way. If you look at Java that was created in 1995, they didn't have those same memory constraints, but they still did sqrt. Python still uses sqrt. Why? Because C did it first. And everybody thinks the square root function is called sqrt, right? So therefore, all square root function versions are called sqrt, right? You also have access in the math library to other constants. m_pi, m_e. What do you think those two are? Hopefully this is obvious. Pi, 3.14159, blah, blah, blah. E is going to be exponent 2.71, whatever it is, right? You have access to those in the math library. Why did they put an m underscore in front of it? Because they wanted to distinguish it. This is the math library pi. If you want to write your own pi, name it something else. If you want to use a library that defines its own pi, right? We don't want a conflict there, right? It's called polluting the namespace, and we'll talk about that later. Okay? All right. We also have another one, by the way, right there. That line right there. That's a preprocessor directive, but it's not including an external library. What do you think it's doing? It's defining a kilometers per mile as a constant, 1.60934, just like pi. If I went to the math library, in fact, can we go to the math library? Generally, what you can do is you can hold down Shift or Control or something like that, and let's see. Yay, we can go to the math library. What does your pi look like? Okay, m_pi. There you go. What did they do? They defined pi to be this big number here, right? What else did they define? They defined a whole bunch of other stuff, right? And that's what we're doing in our program too, right? Imagine if you didn't have that and you had to use pi a lot, 3.14159. What are you going to be doing? Copy pasting that same number. We call them magic numbers. Where the hell did they come from, right? They're just magic, right? And pasting it everywhere. Now, 3.14159, you'd know that because you've been working with pi for many, many years. But if I just gave you this number without any context, 1.60934, would you know what it stood for? No. That's why we're giving it a human readable name, KMS, kilometers per mile, right? Now, arguably, you should have written out kilometers or kilometers in a mile, something like that. You can argue about what the best name is until you're blue in the face. Eventually pick something that makes sense. And that's what I did. KMS per mile. Fine. Right? What it's going to do is the preprocessor is going to go through my program and say, oh, anytime I see KMS per mile, I'm going to do a copy, paste, replace. And it's just simply going to take this 1.60 whatever, and it's going to replace it like that. That's what the preprocessor is doing. It's literally just going through copy, paste, copy, paste, copy, paste, and then it goes to the compiler. Right? It allows me to avoid those kind of magic numbers, those magic mystical numbers of where I do not know where they came from. Right? This is actually called a macro technically, defined as a macro. It is essentially a cut and replace operation by the preprocessor. Macros also allow you to define a single constant, a single value in a single place. What if I want more digits of accuracy? If I've used it in 10 different locations, I've got to change all 10 of those locations. Whereas if I had used a macro to do it, now I only have to change it in one location, right? And every location is using the same value, right? Macros make your code more readable and thus maintainable, and avoiding again, those things called magic numbers. Okay? All right. What do we see next? Line 13. There's our main. Yeah, go ahead.
Is a function declaration for a function called main that returns an integer and takes two parameters, or takes an integer and
Takes an integer and takes a character. That's actually what's called a two-dimensional array. It's an array of strings. We'll get to that eventually. For now, that inner stuff, magic, right? Just know that your main is the main starting point. Every program has to start somewhere, right? And you have a main in C, you have a main in Java, you have a main in Python. If you don't have a main in Python, it just starts from the top, right? But you can put a main in Java, in Python. Yeah? No, you have what are called void functions. In fact, you could do it here too. I don't return anything, but we'll get into that when we get into functions. Right? Right now, as a preview here, why are we returning an integer? Right? And in particular, why are we returning 0? In C, that's for error handling. 0. How many errors were there? None. Right? Everything was great. Right? Oh, there was an error of type 1. I'll return a 1. Oh, there was an error of type 2. I'll return a 2. Right? And then you can have what's called inter-process communication. You can run a program, that program's done, and then you can see, well, what did that program output rather than what that function output. And then you can, do something based on that, right? Nope, the compiler, errored out, right? It didn't work, right? Okay? But otherwise, we'll get into that when we get into error handling. But right now, the main is, again, our main starting point. Every language has every program and every language has somewhere that it has to start. Generally, programs start in the main function or main method, and then we have what's called linear control flow. Once you get into the main, it starts executing commands top to bottom, left to right. So it'll start executing at the top here. It'll execute line 15. There is no line 16 once it gets compiled. It'll execute line 17. It'll execute line 18, et cetera, et cetera. Right? Unless an error happens, in which case it's fatal or something, the program crashes. Okay. What other stuff do you see before we get into the actual working of the program? So what other stuff do you see? Think English, by the way. Right? If I were to write a sentence in English, what would I put at the end of it? A period. That's called punctuation. In programs, we have punctuation. What is my period in C and Java? It's the semicolon, right? And so we have punctuation. Right? Semicolons end executable statements, like sentences. Right? So punctuation. Right? There we go. I'll indent there. Right? What other punctuation do you see in the program? You can go back over here. Brackets, right? What kind of brackets? Talking about these? Yep. So curly brackets, right? What do curly brackets do? They define code blocks. Curly brackets, define code blocks, right? Akin to paragraphs, right? So if you have a sentence on line 15, a sentence on line 17, a sentence on line 18, then packaging those up into a paragraph, right? I have a beginning curly bracket, which has to always have an ending curly bracket here, right? By the way, if you're anybody coming from a Python experiences, right? Do you have curly brackets in Python? Nope. Instead, it is white space. And cross your fingers that the tab and the 4 spaces here, right, it's consistent, because that ain't consistent. A tab and 4 spaces, Python's going to think that those are 2 different things, just like C would think that curly brackets are 2 different things. What other punctuation do you see here? Commas, good. Commas in English separate things, right? I love cake, comma, ice cream, comma, that's the Oxford comma, and donuts, right? We have commas here to separate variable names, right? If I just had this, the compiler might be able to figure that out, but that's not part of the language, right? Compilers are dumb. Compilers are stupid. We want to make it as easy on them as possible. So we say there's this variable and this variable and this variable, right? We also have a comma up here to separate parameters to a function, right? We have a comma over here inside of this scanf call, because the first argument here is a formatting, and then there's another argument over here, right? So we have commas to delimit lists, right? Just like we do in English. Commas delimit lists of things, right? There's separate things. Quotation marks, right? What do I have? I have this, and then inside of this I've got ... whatever you want to put. Quotation marks in English are quotes. So what are we quoting here? These define strings, right? Which are sequences of single characters, like capital A, lowercase a, the character 5, not the numerical value 5, but when we print it out to the screen, that thing that looks like a 5, right? That's a character, okay? What other punctuation do you see here, other than brackets, right? Brackets have an opening and closing. What else has opening and closing? Parentheses, right? Why do we have parentheses in the main, and why do we have parentheses in printf? These are all functions. Let's go back to math. What does a function look like? F of x. What is the function name here? F. What are you inputting to the function? X. And how do you denote that? With parentheses. That's the same thing here. Main is a function, and we denote its input with parentheses. We're calling a function called printf, and we're denoting its input with parentheses. Right? So we always have to have opening and closing parentheses. They always have to be balanced, right? Parentheses, C's, right, denote inputs to functions, just like math, right? Okay. We also have later on square brackets, right? Square brackets are going to be used for arrays, right? That's a collection of things. Don't worry about that for now. What if we did single quotes, though? Right? I don't have any over here, but single quotes. Could I use single quotes over here instead? Python people will say, oh, yeah, that's fine. That's the same thing. But C, Java, no, that ain't the same thing. Single quotes are for single characters. We don't have any characters here, but I can show you how to create a character. Initial is equal to my first initial C for Chris, right? I use single characters there. I could use double quotes, but guess what? That's now a string. It's a sequence of characters of length 1, but that's different, right? That's different than the actual character C. Single quotes are for single characters, right? There we go. Single quotes in both C and Java are used for single characters, like C, my initial there. All right, what don't you see? So this is more of a philosophical thing, I guess. I don't see any exclamation points yet, but we will later. So read between the lines. What's between the lines? Nothing. It's called white space, right? What's the difference between putting no space there versus putting a whole bunch of spaces there, right? It's less readable. That's readable, right? Separating things out with vertical white space, separating things out with horizontal white space. It's a way of making your things more readable. You could write an English paper and never use the space bar, right? And all your words and paragraphs and everything would run together. But we don't do that in an English paper. We separate words with spaces. We separate sentences with 2 spaces. We denote paragraphs by indenting, right? What indentation do you see here? Inside the main, we've indented everything, and we've indented everything over the same amount. 1, 2, 3, 4 spaces here. If I did something different, for example, no indentation there, 2 spaces there, 1 space there, a whole bunch of spaces there, is that readable at all to you? No. What was that tool that I used the other day to fix it? Style. KMS. There we go. Now, it's not going to automatically do it up here. In fact, I don't need this stuff anymore. Let's go ahead and get rid of all of it. But if I reopen it, guess what? All fixed again. Right, nice. If you do that in Eclipse, you can go Shift Command F or Shift Alt F or something, and it'll all be fixed too. I'll show that to you later, though, right? When we translate this over into Java. Okay? All right, so white space characters. White space makes code more readable, right? Vertical white space separates lines. Horizontal white space indents blocks of code, separates things in lists, etc. White space makes your code more readable, right? Make sure that you, above all else, your style is consistent, and unless you have a very good reason to do otherwise, right? White space helps make your code more readable. In general, things at the same level should be at the same indentation level. Again, a parallel to English. If you were to write an outline for your paper, what would you have? Bullet point 1, A, B, C. Oh, sub-point bullet A1, A2, A3. What do? You indent things over because it's all part of that first bullet point, right? You do the same thing in code. You indent and you make sure that everything is consistent. Now, like we said before, there are many different style guides, competing style guides. For example, if you were to use this style 50 up here, they would go with a very old school K&R style of that opening curly bracket should begin on its own line. That's an ancient style. I don't adhere to that. Right? But I don't think any style would allow you not to have a space there. There's always going to be a space there, right? Am I going to grade you based on whether or not you're following the GNU style or the Google style? No. We're just going to grade you based on consistency. If we see that you used 1, 2, 3, 4 spaces, I don't like doing that. I only like using 2 spaces. As long as you keep it consistent and use 2 spaces everywhere, you're going to be okay, right? Now, Java is a different story. Java, there's only one style guide. It's the Java style guide that's already been well established. So let me come over here. What if I don't conform to that style? Bunch of tabs, right? There we go. Right. Then if I hit, again, Shift Command F on a Mac, Shift Alt F, F stands for format, on a Windows system, then it'll automatically go into the Java style for you. Right? I don't think that there are any style guides that say you should have vertical white space everywhere. Just don't do it like, everything should be double spaced. Right? That doesn't make any sense. Most of that is double spaced, but I chose not to do it here. Why? Because this is a chunk of code. These two things belong together. I prompt for the input and then I read the input. It would be far less legible or readable, I guess, if I just had no vertical white space at all. Right? It's still kind of readable, but it looks kind of icky. Right? So declaration of variables, that's completely different from reading in values. Computation of a value, that's completely different from reading in values. Printing, that's completely different from your computation. So, chunk things together, right? If you've got 3 lines of related code, chunk those together, no vertical white space between them. But then you've got this next chunk down here, this next chunk down here. Chunks should be separated with a single empty line. And can I tell you what a chunk is? No, because you could have an idea of what a chunk is. I could have an idea of what a chunk is, and we could both be right. And we could argue about it until the end of the day and not write any code at all, right? So again, that's why we grade based on consistency. Okay. All right, let's see. Let's get into the actual working of the program. All right. What we have first are variable declarations over here. Right. On line 15, what have I done? I've created two variables named miles and KMS. Okay. Before you can you can use any variable, you need to declare it. That's what statically typed means. Okay. Now, if you are coming from a Python background, Python is dynamically typed. You don't have to create your own variables. You can just start using them. Right. I could say miles is equal to 5 without saying double miles is equal to 5 or int miles is equal to 5. Okay. You have to declare them before you can use them. If you don't, for example, if I move this down here after I've tried to use miles, then it would not compile. There. I have no idea what you're talking about miles. Even though it's declared on line 19, you're trying to use it on line 17, it has no idea what you're talking about. So it has to be declared before you can use it. There we go. Let's fix that. There. Okay. That's what statically typed means. To declare a variable, you provide its type and its identifier, its name, right? And we did that with a double. That's what its type is, okay? And then we gave it a name, miles, and then KMS. Those are two variables of the same type. Where you declare a variable is called its scope, okay? Now, if I say scope, what comes to mind? Maybe a submarine scope, right? Where you can only see part of the world at a time. You can't see behind you because you're looking through the scope. If I create this miles here, then its scope begins, it's born on line 15, and then it dies down here on line 24 at the end of the function. That's its scope. It exists from line 15 down to line 24. It doesn't exist anywhere else. Right? So for example, if I were to declare another one, int initial, equal, or let's go with character, is equal to C. Now the scope of that variable is that it's born on line 22 and it dies on line 26. Does it live inside of the scanf function? No, because that's a different scope, right? That's a different thing that they're looking through. So the scope of a variable is where it can be seen, where the program can actually see it. It can't see it above line 22 here, and so we wouldn't be able to use it. Right? That's what a scoping is. What are the basic kind of variables in both languages, by the way? Well, the first one that I'll talk about is an int. Int is short for integer. Now, integers are infinite, right? But a computer is not infinite. Do you have an infinite amount of RAM on your computer? No. You have a limited amount of memory, right? So it's short for integer. It's a 32-bit signed 2's complement integer. Don't worry about that. When you get into a hardware course, you're going to have to worry about it because you're going to have to worry about how those 32 bits work, right? But understand the following, right? You can represent 0, negative, and positive numbers in the following range. Right? Let me go ahead and there we go. Right? Negative 2 to the 31st, dot, that should be C dots, by the way. Let's go C dots. By the way, all these notes will be posted on GitHub. When you view it on GitHub, they'll render the nice little math like this. But if you look at the raw notes, it won't. You're going to see the LaTeX. LaTeX is a typesetting language for math, so don't be confused. Look at if you want to learn LaTeX, great. But otherwise, just know that look at the the rendered one on GitHub. Right? That's about negative 2.147 billion to positive 2.147 billion. What relationship does that have here? 32 bits means that you have 32 zeros and ones to work with. Now, one of them is going to be for the sign. 0 for positive, 1 for negative. That leaves 31 remaining bits. Well, it's base 2, right? Now, if I said that you have 4 digits, what is the maximum value that you could represent there? 9,999. Why? Because you're in base 10. 10 to the 4 is 10,000, but you don't start at 1. You start at 0. So 10 to the fourth minus 1. Here over in computing land, we're base 2. That's why we have 2 to the 31st bytes, right? That's the maximum value that we can represent there. Now, how does it all work, in detail? How do negatives work using this 2 complements? Again, don't worry, you're going to have to worry about that in a hardware class. One more, doubles. And we'll pick it up there next time. What is a double? It is a 64-bit IEEE 754 floating point number. Again, technical babble. Don't worry about it. It's a decimal number with approximately 16 or 17 digits of accuracy. You remember when we looked at pi? Did pi go out to 100 decimal places? No. It went out to about 16 decimal places. Because with 3 there, you can represent about 17 digits of accuracy. What if you want more accuracy? Well, you need a bigger number. You need more bits, right? You need 128 bits. Or you need 5,000 bits, right? Now you're talking about bringing in external libraries for everything. But 17 digits of accuracy, pi out to 17 places, I believe that that's accurate enough to compute a circumference on the nanoscale versus the size of the universe, right? You're not going to need, in fact, in most applications like gaming, you don't even need 17 digits of accuracy. You have what's called a float, which we won't cover, which is 16 bits or 32 bits of accuracy, or I should say like 7 digits of accuracy. That's sufficient to calculate things in gaming down to 1 pixel. Right? Yeah, you first. Go ahead. Yes, you can assign a scientific notation. For example, miles is equal to 1E 10. There, that'll work. That's, what is that? 10 million? What is 10 to the 10th? Or, yeah, okay, something like that. Or you can use a capital E, or you could just use, 0 point whatever, mash your keyboard. Yes, you can use scientific notation in both languages. And your question?
I just wanted to say, I remember NASA did an article on what precision of pi they use.
Oh.
10 digits.
Yeah, the 10 digits is all they need, right? Something like that. So doubles are going to be more than what we need for everything in this class. All right? We'll pick it up there on Friday.